let's look at this very important theorem called Fubini's theorem. Okay, it gives us a way to evaluate a double integral without using the Riemann sum. So this is like fundamental theorem calculus, but for double integral version. Like you don't a way to bypass using the definition of Riemann sum for evaluation. All right, so we know what a double integral is. It's like a function over a region, a given region, and let's call this region R, and I want to evaluate the integral of a given function over a specified region R, and this is double integral. We know this will give us the volume of the solid under the surface given by z equal to f over the region R, right? So that's what we know about double integral. And yet, we're trying to use iterated integral, different way to do evaluation. And Fubini's theorem tells you that, oh, you can use double. You can use iterated integral. So on the right hand side of the equation, what you're seeing is the iterated integral. You can use an iterated integral to evaluate a double integral. So this way, like you know how to do this, and you don't need to use a Riemann sum, right? So you do one integral at a time from inside out. All right. So now the key here is like, when can you use a double this Fubini's theorem? So first of all, the function, the integrand that you have, it must be a continuous function, which is the only case you will be dealing with. And two is you need to be able to describe the region R using inequalities. Okay, so in homework 17, not necessarily homework 17, in iterated integrals, when we're trying to find the area of a region, we know how to use graphs or equations or functions to see a region R. Okay, and so basically it's about formulation. Like if you know the region R can be described by inequalities of x and y, then you will know how to set up the iterated integral accordingly. All right, so ignore the bottom half, so look at the upper half. Okay, so what does this inequalities mean really? So this is what, this is, you have, for the y direction, you have one graph that's given by y equal to g2 of x, and that's the upper limit. Okay, and then you have a lower limit that goes like this, described by y equal to g1 of x. Okay, and now you are only you only care about the y values in between these two curves, right, or two graphs. And then you have like different x values, and here you only wanna worry about the range where x is in between a and b. Okay, so x between b and a, y between g2 and g1, it gives you this region R. All right, okay, so suppose you have a function f over this region R, and you want to find its double integral. Then Fubini's theorem tells you, oh, then what you do is you write this in terms of iterated integral. You integrate f, keep the integrand the same. Don't bother, don't change, don't do anything with the f. Just copy down the f. All right, and then you look at the y direction. Put the lower limit on the bottom, the upper limit on the top, and write dy. Okay, so you're first integrating with respect to y. This is the y direction, right? And then you're going to be like, okay, so I'm scamming from this line x equal to a all the way to this line x equal to b. So now you integrate it with respect to x, going from a to b. Okay, and once you have the iterated integral set up, then you just do straightforward computation. Similarly, if your graph now looks like this, the region R, if it looks like this, okay, so x is in between the function h1 of y, so h1 of y, let's say it's this one, and x is equal to h2 of y. Okay, so this is y. All right, so you only care about the x values in between these two curves. Okay, so for each y value, you have a lower limit for x and then upper limit for the x. And the lower limit and upper limit depends on the functions h1, h2, and the y value. Okay, and you only care about the part where y is between a number c and a number d. Okay, so this is y equal to d and this is y equal to c. So now we are then looking at a region that's like this. Okay, all right, so in this case you can see that you are slicing the region along the x direction first, and then you're gonna scan it through the y direction, right? Okay, so in this case the double integral will be evaluated by this iterated integral, where you integrate with respect to x first, and then you scan through the y direction, so integrate with the y layer. Okay, lower limit h1 on the bottom, upper limit h2 on the top, c and d, lower limit c on the bottom, upper limit d on the top, like that. Okay, so you're gonna see more examples how we implement this Fubini's theorem. Okay, but this is just a general structure. You can compare the general structure where we evaluate area of a region R. Okay, so we have a video talking about that. Like when you have a region R and you can describe this region R by inequalities, then you can just find the area by setting up a corresponding iterated integral like this. In that case, you will have f equal to 1, right? So this is just basically a variation for the case how we use iterated integrals to evaluate the area of a given region. All right.